guys, so to start off here, we can break down all the trigonometry you need to know for the Pure 11 paper into 5 sections. Let's dive into section 1, special triangles. From GCSE level, you should already be aware of the following ratios, so I'm not going to go into too much further detail on that. What is important here though is the square you see on the screen in front of you. Why? Because in the exam, you'll get questions where you'll come to a result like this and they'll want it simplified and you won't know what to do. Understanding the nature of the square will help you to figure that out. So now that we know this square is important, how is it important? Well, let's cut it diagonally. What do you see now? A right angle triangle. That's right. Let's say now that the length and height of the square is 4. Therefore, our hypotenuse here, according to the Pythagoras equation, is root 32, which can then be simplified down to root 16 times 2, which can be simplified further to 4 root 2. Okay, cool. Now, add to this that because we cut our square in half, our 90 degrees now turns into 45 degrees in this new triangle. Therefore, we can say that sine 45 is equal to 4 over 4 root 2, which means that sine 45 is equal to 1 over root 2. So what? You're probably asking. Why are you showing me this? I'm showing you this because we've just arrived at a key principle. What we just did can be applied if the length and height were 9, 1 million, or 465.7843. Basically, from this triangle we can say that sine 45 is equal to 1 over root 2. Cos 45 is equal to 1 over root 2, and tan 45 is equal to 1. The next group of crucial ratios to understand is derived from the equilateral triangle you see on the screen in front of you. As you can see, it has a length of 6 for each side. Similar to the exercise we did before, let's split this in half. And as you can see, we are now left with 3 angles here: 60 degrees, 30 degrees, and 90 degrees. But still, our triangle is incomplete, as we don't have this value, so let's fix that. To get this side, we do 6 squared minus 3 squared is equal to 3 root 3. Therefore, sine 30 is equal to 3 over 6, which equals a half. Sine 60 is meanwhile equal to root 3 over 2. Cos 30 is equal to root 3 over 2, and so on and so forth. And as you can see, similar to before, the length here doesn't matter because it always simplifies down. From here, it's clear then that the following values will always remain true. Why? Because we've illustrated that no matter what the size of the triangle, if the conditions of the angles apply, the ratios will also always apply. To make things visually easier, simply remember these triangles and you'll be able to get the values whenever you need. Alright, so now this part is critical. And that's because you'll start to get questions where you get angles that don't necessarily fit the classic right angle triangle blueprint. And so therefore you need to reframe the way you think about trigonometry. From simply a method to find angles and sides within a triangle to what sin x, cos x, and tan x actually are. Functions. What does this mean? Well, this means that as functions, they can be graphed. And when we apply the graphing process, we get the following. For sin x, as you can see, the domain is 0 to 360 degrees, whilst the range is -1 to 1. Now a similar story can be said for cos x, where the domain is also 0 to 360 degrees, and the range here is -1 to 1. When we graph tan x, however, we get a very different answer altogether. And that's because we have a period of 180 degrees and a range going from infinity to -infinity, which is why we have these jagged lines. But the important thing to note here is that yes, we can have multiple angles in the context of trigonometry and not just be confined within right angle triangles. This now leads me to the next thing you need to know, the cast diagram. As you can see, it's a classic axis with both positive and negative values for both x and y. To make things easier, what I like to do is to actually draw right angle triangles within the different quadrants. You'll see why in a second. In the all section, this means that all trig angles in this quadrant are positive. Why? Because as you can see, both the x and y coordinates are positive, which means that no matter the size of our right angle triangle, we will always get a positive value for theta. If we go here now to the S quadrant, this means that only sine theta is positive. And that's because sine theta is equal to opposite over hypotenuse. Well, so what? Well, the opposite will never be negative, and the hypotenuse will never also. Meanwhile, cos theta and tan theta will be negative in this quadrant. Following this trend, for our third line, you can clearly see that only tan is positive. Why? Because we have two negatives on top of each other, which therefore turns our equation into a positive as a result. On the contrary, as you can see, both sine theta and cos theta are negative. Lastly, for C, we follow the same pattern, where only cosine is positive. Why do we do that? Well, we do that because the x-axis is always positive, as is the hypotenuse. Now, okay, you've got the background here, but where can this actually be applied? Well, we'll get to that later, so make sure to stay to the end. Now let's go back to why I'm showing you these triangles. I'm showing you these triangles because, as you can see, a relationship is clearly formed between both the acute angle within the triangle and the related obtuse angle next to it. So for instance, if our acute angle in this quadrant is 30 degrees, our corresponding obtuse angle is 150 degrees. So now you may be saying to yourself, well, okay, but so what? How does this relate to me at all? Well, as mentioned before, this core principle will be central to solving trigonometric equations, which we'll get to in a little bit. Alright guys, so now we're really getting into the nitty-gritty of the stuff, because we've come to the concept of trigonometric identities, which is so important, not only for this syllabus, because it makes up such a large percentage of the questions you'll get, but for any trigonometric question in general. So, what are these identities? Well, luckily for the AS exam, you only really need to know two. The first is sine squared x plus cos squared x is equivalent to 1. And the second is tan x is equivalent to sine x over cosine x. Don't worry about proving these identities. That's beyond the scope here. However, what is crucial is that you know how to weave the different identities into each other and ultimately prove the trigonometric identities. For example, you may be asked to prove that 1 plus tan squared x is equal to 1 over cos squared x. Can you see how we may be able to find the solution here? Pause the video and give it a try. The question that arises first is, which do you want to unpack in order to solve the identity? Left hand side or right hand side? As you might have figured out, tan squared x can simplify down to sine squared x over cos squared x, which is nice and simple. So as a result, I will pick left hand side to start. Unpacking this then, we get 1 plus sine squared x over cos squared x, which then, using the common denominator of cos squared x, gives cos squared x plus sine squared x over cos squared x. But now there's another issue. Can you see it? How can we simplify this now? We have a sum at the top and cos squared x at the bottom. Well, that's a fine question with a fine answer, because our solution here is to simply recognize that cos squared x plus sine squared x simply becomes 1, which means our answer is 1 over cos squared x. Therefore, we can finalize this by saying that left hand side is equal to 1 over cos squared x, and we can therefore conclude that left hand side is equal to right hand side as required. Now this is a very simple example, so I'll make sure to dedicate a different video on some harder questions surrounding this, but the point stands. You need to know how to weave those existing identities into new forms to generate proofs. Remember how before I mentioned that our trig ratios are actually functions and can be represented therefore graphically? Well, what happens when we apply transformations here? What happens to the graph at hand? Let's take a simple example. Say y is equal to sine x. If we multiply it by 5, for example, our range now magnifies to be between both -5 and 5. Now imagine we start to mess around with the angle. What happens then? Well, let's imagine we multiply that angle by 2, so we now have y is equal to sine 2x. As you can see, our domain has clearly been impacted. How exactly? Well, it's halved. The graph repeats every 180 degrees instead of every 360 degrees. And what if we add something to the angle within y equals sine x? What then? Well, let's say we have y is equal to sine x plus 90 degrees. Well, in this case, our graph actually shifts to the left, like this. And meanwhile, if we do the opposite, y is equal to sine x minus 90 degrees, our graph shifts to the right instead. This is pretty simple stuff, and its usefulness can be derived from the fact that you'll sometimes just get questions asking you to draw a graph. So for example, you need to know A, the graphs at hand, and B, the manipulations of these graphs. Okay, cool. So now we have an idea of the nature of trig graphs, but the question is this. What happens if these are now flipped? How do things change exactly? Well, the inverse functions look like this, with the horizontal and vertical elements switched. But this doesn't really give us much to work with in an exam context. So how do we make use of this knowledge? Most of the time, you'll be asked something like the following. Sketch sin x and explain why it has an inverse function. This is where your knowledge of functions, a different part of the syllabus, comes in. In order to explain that sin x has an inverse, you need to recognize that for a function to be inverse, it must be 1-to-1, which arc sine of x clearly is. And as you can see, the domain of sin x equals the range of the inverse of sin x. And the range of sin x is equal to the domain of the inverse of sin x. So what? Well, where this really comes in useful is when you're asked to actually find the inverse itself. So for instance, if we're given y is equal to 4 sine x over 2 and told to find the inverse, our process is as follows. 1. Swap x and y. So now we have x is equal to 4 sine y over 2. 2. Next, make y the subject. So we have now x over 4 is equal to sine y over 2. 3. After this, apply inverse sine to both sides, which means now that we have arc sine x over 4 is equal to y over 2. 4. From this now, we can therefore say that y is equal to 2 arc sine x over 4. Okay guys, now for the last, and arguably the most important section, we have trigonometric equations. This is so important because for the equations, everything basically ties in together. Let's say for instance, we're given a question like this. 2 sine x is equal to 1 plus cosine x, and we're told to solve for x such that x has to lie between 0 and 360 degrees. How do we proceed from here? Well, as you can see, there are 2 different trig functions present. So what do? The first thing we need to do is isolate both functions, and when we do that, we get 2 sine x minus 1 is equal to cosine x. But now, what do? We can't break it into tan x equals sine x over cos x, and meanwhile sine squared x plus cos squared x equals 1 is nowhere to be seen here. So is that it? Is all hope lost? No. If we square both sides, we can get 2 sine x minus 1 squared is equal to cos squared x. Now, we have something that we can work with, cos squared x. And what can that become? Well, remember cos squared x plus sine squared x equals 1. So therefore, cos squared x is equal to 1 minus sine squared x. Plugging this in, we therefore get the following. 2 sine x minus 1 squared is equal to 1 minus sine squared x. If we expand this and then simplify this, we therefore get to 5 sine squared x minus 4 sine x is equal to 0. Okay, great. So we have a simplified function in front of us, but now we need to solve it, which means we take out sine x, which leaves us with sine x times 5 sine x minus 4 is equal to 0. But now we have another problem. We have two answers for sine x. Well, in the case of sine x equals 0, if we solve for x using our calculator, we get 0. Is that it? Or no? Remember our work with trig functions. If you look at the trig graph, it's obvious that x can equal other values too. In this case, 180 degrees or 360 degrees, all within the range given in the question. So that's all good. In the second case, we have 5 sine x minus 4 is equal to 0, which means 5 sine x equals 4, and therefore sine x is equal to 4 over 5, which equals 0.8. But remember, from our trig graphs, we know that sine x is a function and can therefore have multiple values. From this, we can go onwards to our quadrant, and therefore since 0.8 is obviously positive, we can put it in quadrants 1 and 2, which means x is equal to 53.1 degrees, as you can see from the triangle, or x equals 180 minus 53.1 degrees, which equals 126.87 degrees. As a result, we have 4 solutions: 180 degrees, 360 degrees, 53.1 degrees, or lastly, 126.87 degrees.